Now, parallel computation is at the heart of big data computing. However, to specify what becomes parallel, we usually think of a conceptual model of parallel computation, often called a programming model. A parallel programming model is a way to specify abstractly how a parallel program will run. Naturally, for a program to be parallel, there must be a number of concurrently operating processes. But how do these processes communicate and exchange data? How do they decide when to communicate with each other? Further, what exactly is done in parallel? To think of the first question, two processes may communicate data by sharing memory. Indeed, there are architectures in which all memory in multiple machines can be made to virtually look like one large addressable memory space. However, two processors may also communicate by passing messages to one another, either directly from one process to another or through a common message carrying pipe, often called a message bus. The second question can also have multiple answers. Two of the most common ways of achieving parallelism are task parallelism and data parallelism. In task parallelism, a large task can be decomposed into multiple subtasks, each of which can run concurrently. In data parallelism, the data can be partitioned into many smaller fragments, and operation can run on each partition independent of the others. Typically, these partial operations are then synchronized and partially processed data combined to produce a full answer. Many parallel data management systems operate in a partitioned data parallel manner. We need to remember that task parallelism is somewhat independent of data parallelism, and it is possible to have both forms of parallelism in a programming model. It is important to emphasize the issue of a programming model should not be confused with the issue of a programming language. A programming language is independent of the programming model, and therefore a programming model can be implemented in several different languages. As I mentioned, the programming model we are going to consider is BSP. BSP wasn't initially created for graph computation. It was thought of as a parallel computing model that will bridge the gap between software models of parallel computation and hardware capabilities for supporting parallelism. The basic idea of BSP is as follows. There are a number of processors. Each processor can perform local computation using its own local memory. There is a router which can serve to pass a message from any processor to any other. When one pair of nodes are exchanging messages, another third node can still perform computation. There is a facility that can synchronize the state of all or a subset of processors. This synchronize may either happen periodically at intervals of L time units, or there may be another way of specifying when the synchronization is going to happen. But when it does, all processors affected by it will come to a consistent state. When synchronization is performed, a fresh round of computation can start. We call this synchronization point barrier synchronization, because all executing processes must reach this barrier point before the next step of processing can continue. A BSP program is broken up into a sequence of super steps. In each super step, each processor will get the data if needed, perform its computation if needed, and then exchange data with the right partner. Once all the nodes are done, the system helps to synchronize. Then the next round starts. Each processor can determine if it needs to compute or exchange data. If not, it will make itself inactive. If required later, a processor can be woken up to be active again. When all processors are inactive, the computation stops. Now, in applying BSP model to graphs, we make a few assumptions. We assume that a processor is synonymous with a vertex. So a processor can only send messages to or receive messages from its neighboring processes. We also assume a vertex has an ID and possibly a complex value, and an edge may also have an ID and a value. Each vertex knows which edges it is connected to. We can now think of a computation as a vertex-centric task. We'll shortly show what this means. In a now famous paper from Google, This programming model was called think like a vertex. Well, to think like a vertex, we need to know what a vertex can do. Here's a list of actions a vertex can take. The first one is easy. A vertex can find its own identifier. The second operation is to get or set the value of the node. This operation may be a little involved if the value is a complex data object. For our purposes, we will assume the value is a scalar. Next, a node can ask for its own edges. The result of the operation is a set of edge objects. A node may also count its edges. Since we are referring to outgoing edges throughout, this is the out degree of the vertex. Recognize that this means a vertex does not natively have access to its incident nodes. However, it does have control of the outgoing edges, so it can get and set the edge values. There may be two different ways of specifying an edge. The edge may have an ID that the node can get. Possibly more commonly, an edge is identified the vertex it targets. So in our diagram, V1 will ask for the edge targeting V4. So in a situation like V3 and V5, where there are multiple edges between V3 and V5, the source V3 can ask for the values of all edges going to V5. The update operation can add or remove an edge of a vertex. Finally, since the vertices are processes, they can start or stop computing. Typically, a node wakes up if it receives a message from another node. Now, in comparison to a vertex, an edge can do far less. It can get its own ID if the system allows edge IDs. It can set and retrieve its own value, and it can get the ID of the node it's pointing to. That's it. Now, we still have not defined how to think like a vertex. That's what we will do next, using an example that we have seen several times before. It's Dijkstra's single source shortest path SSSP algorithm. We have seen this algorithm before, but now we'll show how to compute it in a parallel setting using BSP. Here is the edge value. That's the weight of the edge. This is known before the algorithm starts. Each vertex runs the exact same routine concurrently. So each vertex asks, 1, is it superstep 0? 2, if yes, then if this V is the source vertex, it sets the value to 0. Else, it sets the value to infinity, which is a large number. The source vertex propagates its edge value to the nodes at the other end of the edges. Just the source vertex. All other vertices are quiet. The propagation process works like this. A vertex gets its own value, which for the source vertex is 0. It gets its edges. For each edge, it gets the value of the edge, adds it to its own value, and sends the result to the endpoints of the edge. The blue numbers indicate that the messages are sent. All vertices vote to halt. That is, they now have hit a synchronization barrier. Notice that the receiving nodes do not look at the messages yet. It's the system's job to ensure that the messages are available to these nodes at the next superstep. All nodes who have received messages wake up and read the messages. If a node receives multiple messages, it picks the minimum. In our case, the two active nodes have received only one value each. We have, for the sake of convenience, colored the processed edges in yellow. This is just for visualization purposes in this example. Now, it compares this minimum value to its own value. And if its own value is greater, it sets its own value with the minimum value. In our case, both nodes set their value to that of the incoming message. The same propagation routine works again. So, each node computes the new distance and sends the message along an edge to the other endpoint, then halts. The same step is repeated in the next superstep. At this point, the nodes have updated their values. The node with the value 6 has received a message just along one of the three edges incident on it. Continuing, at the end of superstep 2, all nodes are ready to receive messages from all their incident edges. The node with the value 6 received a value which is lower than its current value. Now the active nodes have no more messages to send, so each vertex votes to halt. The vertex ID and the value are read out from each vertex, and then the process stops. If these nodes are on different machines of a cluster, the system will rely on the underlying platform like Yarn or Spark's underlying infrastructure to ensure that the edges going across machines can send and receive messages effectively. This should give you a sense of the speed of this process for a large-scale network.